Okay, so let's do an example problem as far as oxidation is concerned, just to make sure that we understand what's happening here. And this example is going to say draw the oxidation products of D-iodose. And notice it doesn't tell you what you've oxidized with, right? It doesn't tell you bromine, it doesn't tell you toluenes, it doesn't tell you nitric, it doesn't really give you any kind of guidelines. And that's why this says products, not product, because it wants you to kind of understand that you can get different products depending on the reagents that you choose. So we want to show all of them if we can. And really we're kind of focused in on bromine and nitric acid. Toluenes not so much. I mean, toluenes is there. We can kind of show toluenes. It's not that big of a deal or that big of a change, but we'll at least include it into the bunch. But they're really after the actual bromine product and the nitric product. So before we can do this, we have to kind of figure out what D-iodose structure is going to be, right? And this is not one of them that I told you to memorize. So you need to find this chart, find it in the chart, draw it on the actual sheet of paper when you do find it. And the structure of D-iodose, it is an aldose. So we have a C double bond OH up here at the top. And this aldose has 6 carbons in it, so it's a aldohexose. And down here at the bottom is a CH2OH group. So this is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and this makes my 6th carbon. If I look at the position of the OH groups, I'm going to find out that aldose has 1 to the left, then it has 1 to the right, then it has 1 to the left, and then it has 1 to the right. So this is the structure of D-iodose, and this actually will tell me at least where to start. Okay, so we know that 2 oxidation reactions can happen at least. Those are the ones we're going to be focused on. One of these is going to include the bromine route, and one of these is going to include the nitric route. So I want to draw the structure that would happen if bromine is used for the oxidation. And this is kind of easy once you know the starting product or the starting reagent. So I'm just going to draw iodose all over again. I'm not going to change anything at all. So this is left, right, left, and right. And once I get this structure of D-iodose, bromine only oxidizes one end, and it's the end with the carbonyl. So this is the aldehyde end, and this changes into an OH group. So that's what bromine will do, right? That's the difference between the product and the reagent. This is a carboxylic acid end now, and not an aldehyde end any longer. With the nitric acid, it's as easy as that was, right? This is a C double bond OH, and then I'm just going to replicate the structure of iodose. So this is left, right, left, and right. And nitric acid is a strong one, strong reagent. So it's going to target the top, and it's going to change that into an OH just like bromine did. But you know, it's also going to target this down here at the bottom. And this CH2OH also turns into a C double bond OOH. Okay, so this is the route for the nitric acid. We actually see a change that happens here, and we see a change that happens here. And those are your products. Now keep in mind there's one carboxylic acid group here. So this creates our aldonic. We can kind of see the word one involved, acid. And this creates 2 carboxylic acids. So there are 2 carboxylic acids on that product, and this is called an alderic. There are 2 groups on the structure. So there's our aldonic acid and our alderic acid product. If I wanted the toluenes reagent, the only thing that happens with the toluenes reagent And I can come down here, and I'm just going to put this on a dotted line. If I was required to predict the product for the Tollens reagent, I would start off with the structure of aldo or idose yet again. So C double bond OH, CH2OH, and then here we have left, right, left, and right. And if I wanted to draw the product for the Tollens reagent, the only thing that the Tollens reagent does is the entire molecule stays the same. There's nothing happens to the entire molecule. And what goes on is that an oxidation step happens because it is classified as an oxidation reaction. And instead of an OH going on up here at the top, an O goes up there at the top. You got to keep in mind this typically forms a carboxylic acid, right? These are carboxylic acid groups up here. But the Tollens reagent is made in a basic environment. You've got some ammonia and you've got some hydroxide. So it tends to pull off that acidic hydrogen because that hydrogen is very easy to be ripped off by a base. It's acidic in nature. So that's why we are left with an O- there as far as the Tollens goes. So that's the only difference between these three. That's it. Now I don't want you to get confused, because there's another way that we can draw this C double bond OOH, and we can write just COOH, and that is understood to basically be C double bond OOH. I mean, that was one of the very first things that you learned, or that you should have learned, in organic chemistry, period, right? The very first chapter or two talked about what these things look like Lewis structure-wise. So the C double bond OOH is the same thing as choo-choo, right? Almost COOH. And we can kind of shorthand and clean this up a little bit as well. We get the COOH group at the top, and then we get this COOH group down below, and we get an OH group left, right, left, and then right. So that means the same thing. I don't want that to throw you off. COOH is the same thing as a C double bond OOH. Okay, so there's an example of maybe these oxidation reactions. You know, you're going to find these questions in the textbook. You're going to find these questions on the homework. The only thing that they will do maybe is that they will want you to go through and name them. So keep in mind that this is idose. It came from idose. So when we make a aldonic acid, we end up with an onic ending. So really, if I wanted to name this, I need to name it as a onic acid. Well, what type of onic acid? You use the prefix of the sugar that it came from. So if this came from glucose, you would end up with gluconic acid. Because this is idose, this is idonic acid, right? So if they do ask you to name it, that's the way that you do it. The same thing down here for the alderic acids. They end up in aric acid, right? So aric, let me erase this, spelt that wrong. A-R-I-C, aric acid. Well, if this started off with glucose, it would be called glucaric acid. But we didn't. We started off with idose. So this is going to be called ideric acid. So that's how you would name them if you were requested to do that in a question, especially in the homework through Mastering Chemistry or on Blackboard through a quiz or a test. So that's the issue. Sometimes they will ask you to draw them or pick a structure out from the list. Other times they will ask you to name it or pick out a name from the list, and that's how we would name them. Onic acids and aric acids. The root word comes, for this prefix comes from the type of sugar that made it. Okay, so congratulations, you're done with oxidation, reduction. We're now finally going to move on, and the next reaction that we're going to concern is called Kalani-Fisher. So I always love fancy little names for reactions because, it makes me sound good, it makes me feel better about myself. Kalani-Fisher, just saying that makes your mouth smile, and showing this reaction is going to make my fingers happy as well. So we'll do Kalani Fisher in the next video and we'll see what that's all about. So stay tuned, good luck. I'm glad you're here. Bye bye.